Now let's talk specifically about each of the intermolecular forces. We're going to start with dispersion forces. And there we go. Lost my marker for a second. So we've got dispersion forces. And we'd already said that these can't come from temporary dipoles. So let's talk about how those might arise. So let's imagine we have a molecule with a nucleus. It's got some positive charges and some neutrons in it. Well, I'm just going to draw a single thing for the nucleus like this. And then let's say it's got an electron over here and an electron over here. Okay, everything's about the same. And over time, these electrons move around. So sometimes maybe the electron's here and an electron's here. That's about neutral. But then just due to random motion, what happens is we get where one of the electrons is over here and one is over here. Well, now we have a partial negative charge on this side and a partial positive charge on this side. So let's draw like that to represent the whole atom. So now what happens is this partial negative and positive charge are going to interact with other molecules around it. So imagine if we have two next to each other, and well, this one's got two electrons on this side, which has got, and the nucleus should be in the middle. I'm just a very bad drawer. And then we put another one of those molecules near it, and its electrons are going to want to go to this side as well. That way, the partial positive side on this side interacts with the partial negative side of the other one. And these should be the same size. You get the idea. So this is why we pay people to make textbooks, and I would not hand draw them. But this is the basic idea. So we end up with these negatives and positives near each other, and these can make a long chain of these. There doesn't have to be two of them. They keep interacting with the molecules around them. So this leads to an interactive attraction because, hey, now these things are close together. This is a stabilizing force. We've got some positive on one side and negative on the other. And so this makes it more attracted to each other. Now, over time, because the electrons can move around, these can end up rearranging themselves somewhat, is that the electrons can move away, and then it changes the orientation of the molecules. So this is not going to always be exactly this shape, which is different from our dipole-dipole attractions. So when we have permanent dipoles, then one side's always going to be negative and one is always going to be positive, and that's going to look different. But here, we're dealing with temporary negative and positive sides, and they may not be as strong, right, because it's of an attraction as well, because there's not as much charge difference in many cases. So this gets us to these. So this is going to be one way that we can get interactions between molecules. Even when they're nonpolar, they still have electrostatic attractions because of instances like this. Now, another thing to point out is because all molecules have electrons, because the only thing that's not going to have electron is something like a hydrogen ion by itself. So once we've got a molecule, as long as we have at least one electron, that electron can move around, and we can end up with dispersion forces. So all molecules can have dispersion forces, because I'm assuming we're talking anything that has at least one electron, which covers just about everything. So any molecule you're working with is probably going to have at least one electron. At that point, it can have a dispersion force. This is true even if it also has a dipole-dipole force. So as long as there are electrons, this can happen. So all our molecules are going to have dispersion forces. It's just some molecules will be impacted by other forces as well. So what determines this? So this is related to what we call the polarizability of the electron cloud. So what we mean by this is how easy is it for it to build up a charge so that one side is more negative and one is more positive. And to do this, this is related to the volume of the cloud. And the easiest way to see this practically of how it comes up is that we look for molecules that have larger molar masses. So if a molecule has a larger molar mass, it's going to lead to more electrons, which is going to lead to an increased volume of the cloud, which means it's more polarizable. Polarizable. Cloud, which means more polarizable. I mention all these steps because in terms of solving problems, it's very much one step. I compare these two molecules. This has a bigger molar mass than this one. It's going to have stronger dispersion forces. But I think it's important to understand the reason behind that. That's because as the molecules get larger, they've got more electrons. So the more molar mass means they have more electrons, means they have a larger volume. That's what allows there to be a polarizability difference. The other thing that comes up sometimes is the shape of the molecule. So if you have more surface area, then there's going to be more places where you can have an induced dipole. So more surface area equals larger area for a dipole, which means you're going to have stronger attractions. Now, of these two, I'm going to talk about shape first. So in 1212, there aren't as many instances where you can easily deal with shape. So in terms of it's impactful, it's important, just like the polarizability is, but I'll be the first to tell you, it is harder for us to ask questions about it. So I want to give an example of how we can. So I want to look at two molecules. So let's look at N-pentane versus neopentane. What happens here is N-pentane, so this is where you've got 5 molecules and they make a chain like this. Well, that molecule's long and spread out, so it has a lot of surface area. So when those pentane molecules interact with other pentanes, they can stack on top of each other, and so they've got a bunch of space that they can interact. But if you take neopentane, where one of the carbons is in the middle, and you make a small sphere instead, that sphere, instead of that oval-like shape, I don't remember what the three-dimensional name for an oval is. I really should. This is one of those things I'm going to go back and listen to this video and be like, I know what that is. That was silly. But so our spheres, they're not going to have much contact area. So in terms of surface area, it's specifically surface area where they can touch each other. So you should be careful how I say that. Because our sphere has a large surface area, but when I try to put the two spheres next to each other, there's not as much space for them to be able to interact with each other. So at that point, when they touch, there's not as much area. I can't have as strong of a dipole-dipole force. So those are going to end up with weaker forces. Now with size, that tends to be easier to see. The idea is we look at molar masses and we compare them. So for example, let's say we took the noble gases, helium, we got neon, argon, krypton, and xenon. And if you look all these up, as you go down, molar mass goes up. Now what also happens, if you were to go down there, you have another trend. Their boiling point increases. Now, when I say that, so the boiling point goes up as the mass goes up here. Now, one thing you might be asking yourself after that is, okay, you told me the boiling point went up. We're talking about dispersion forces. Why is that related? Good question. Many times, the way we're going to talk about the strength of the intermolecular forces is not just by, what's the intermolecular force strength? We're going to ask some property that is based on that. So, this is how they're related. As, I'm going to say intermolecular forces is IMF. I'm sure it stands for something else as well, but as our intermolecular forces increase in strength, the boiling point increases. And let's talk about why. So, as our intermolecular forces increase, that means the molecules are more attracted to each other. What happens when we boil things is the molecules are changing from a liquid to a gas. In the liquid shape, we said that they're really dense and they're all close to each other. When they're dense and close to each other, they're interacting with each other. They have intermolecular forces because they're right next to each other. But when we evaporate and turn into a gas, when they vaporize, well, now they're far away from each other. So the intermolecular forces aren't close enough, they don't get to interact with each other. Remember when we talked about ideal gases in 1211, we even mentioned the idea that we assumed for an ideal gas there was no electrostatic interaction at all, that the molecules just flew right by each other. So in that case, once things get away, they don't get to interact anymore. They don't get that stabilizing factor. So it takes more energy to get a substance to boil when it likes itself, when it likes to interact with itself. So as the intermolecular forces increase, then it's going to hold the molecules together. They're going to want to stay at either the liquid or the solid phase longer. It's going to take more energy to break apart those intermolecular forces and decide, you know what, you have enough energy, the molecules are going to escape anyway. So this is a way we're going to talk about intermolecular forces. The question will sometimes be, which has the strongest dispersion force? But in other cases, we might just ask, which of these has the highest boiling point? And your goal is for you to identify, higher boiling point means stronger intermolecular forces. It's a two-step question. where we're not always mentioning that second step. So we have to make sure that we're okay with that. Now, one other thing I want to bring up here is something that I've noticed some textbooks just kind of assume that you know, but we don't ever actually teach, which bothered me a lot. So when you deal with these molecules, the way they're going to be drawn is sometimes not obvious. They're going to use this stick notation. For example, you might see molecules that look like this. Or you might have a molecule that looks like this. Or maybe we have this molecule here. Or maybe we have, that's enough for now. So what's happening? When we draw molecules that look like this, every single one of these points where I change places, or I change directions, represents a carbon atom. So this represents 4 carbon atoms. The other thing we assume is that every one of those carbon atoms, if there's nothing else in the drawing, like some electrons or another letter, each of those carbons has the right number of hydrogens to give it a full octet. Because it's drawn, that's not a valid Lewis structure, right? Like these carbons either have 2 or 4 electrons. So they're also, the end carbons here will have 3 hydrogens, because that gives them 4 bonds. These carbons will have 2 hydrogens. Now, something that may be obvious pretty quickly is there's a reason that textbooks like drawing the top picture, not the bottom. The bottom gets very unwieldy very quickly. So this notation is important for asking things like which has the strongest intermolecular force. Because if I just asked you which of these 2 that I'm drawing now has higher molecular forces, if you didn't know what they represent, you might not know. But once you do, oh, the second molecule has more mass. It's going to have stronger dispersion forces. It's going to be the strongest. So it's going to have the highest boiling point, or a bunch of other properties we'll go over in a video or 2. So that's the first thing you want to know about these drawings. Now, sometimes they'll have letters in between, like this oxygen here. This molecule represents still carbons at the end, but now we replace one of them with an oxygen. And these carbons at the end still have the hydrogens because there's no other letters around them. Now, oxygen is normally going to have 2 lone pairs because it started with 6 electrons. So once it's bonded twice, it's still going to have 2 lone pairs on it. And that'll give it its full octet. So we get something that looks like that. And then this OH version, we have a carbon connected to a carbon connected to an oxygen. But now this oxygen has a hydrogen on the end, they're telling us. And then it's going to have 2 lone pairs because that'll fill it up. And these carbons will have their hydrogens. So I know this is not the neatest drawing in the world, but you can get the idea. So this is a way we're going to draw molecules in 1212 now sometimes. As you get into organic chemistry, you'll go into way more detail than what I just did, and you'll get really good at drawing these figures and knowing what they represent. But I think this is enough to help you with some of the problems in 1212, where it kind of gets assumed, oh, they'll pick this up somewhere, but I don't think it gets covered in enough detail. So I wanted to explicitly mention this, that this is what these drawings mean. So I think that's enough to get us through our dispersion forces. So now what I want to look at is our dipole-dipole forces. So for dipole-dipole, this is going to occur between polar molecules. So polar molecules. So for example, let's take, I like this example that one of my textbooks used I worked with before. So we've got C double bonded to an O connected to 2 H's. Formaldehyde. Oxygen is much more electronegative than the other atoms. It's going to have a partial negative charge. This carbon, hydrogen, hydrogen here is going to have a partial positive charge. Now, what we can do now is, since we have a partial negative and a partial positive all the time, is, hey, another formaldehyde, it would probably arrange itself like this. And if we had another one, it would arrange itself like this. And note, it was assumed that the lone pairs were there, but I'm going to go ahead and draw them because I think it's good practice, especially when you're not super confident in it yet. So they're going to arrange themselves in this line, where the negatives are attracted to the positive ends and the positives to the negative ends. And these attractions don't have to worry about the electrons moving around and changing where the charges are and then suddenly needing to flip some of them, because the oxygen's always going to be negative and the carbon-hydrogen side's always going to be positive in this molecule. So this leads to a attraction. It's important to note that on average, our dipole-dipole forces are going to be stronger than dispersion forces. So if you have 2 similar molecules, but one has dipole-dipole interactions and one does not, you're going to end up with something where the dipole-dipole forces have a higher boiling point, and they've got stronger intermolecular force interactions. So what's a case where this comes up? We'll actually take this formaldehyde. So formaldehyde. And then we're going to compare it to ethane. So ethane is this molecule here. Now, between these two molecules, it's interesting to note that they end up having very similar molar masses. So they both have a molar mass of about 30 grams per mole. But if you were to look at them, I got to get some numbers up here. Their boiling points are drastically different. So formaldehyde has a boiling point of negative 19.5 degrees Celsius. Ethane has a boiling point of, if I can read correctly, it's negative 88 degrees Celsius. It might be 68. Both give the same idea, but I'm pretty sure it's negative 88. So these are their boiling points. Remember, we said boiling points were a good way to talk about strength of the intermolecular forces. So our formaldehyde boils at a higher temperature. Remember, these are negative, so it's closer to 0 degrees Celsius. The reason for this is because that dipole-dipole force is stronger than the dispersion forces. And they have similar molar masses. Their dispersion forces would be about the same. They contribute about equal to those. It's just the dipole-dipole that ends up making the formaldehyde have stronger intermolecular interactions there. So, another thing I think that's good to do is to make sure we're good at being able to identify whether a molecule would have a dipole-dipole force. So let's take these examples. Let's take CH4, CH3Br, and CBr4. Now let's do CO2 for good measure. I want you to try to identify which of these has dipole-dipole forces and which doesn't. So pause me and give that a try. Okay. So now let's look at these. So what I'm going to tell you right away is this one has dipole-dipole forces and none of the others do. Let's talk about why. So CH4 I don't have a CH4 built. I have a molecule kit, but I'll do this. So, as an aside for anyone watching this, I am making a polarity video as well. If you're not finding it through my course tip, but just found this by going, check out that video. I'm going to do some molecules in that, and we'll talk about why certain ones of these are polar or not. So that'll be in my polarity video. So I'm just going to say here, my CH4, what's important is the carbon-hydrogen bond is nonpolar. They're so close in electronegativity. So we have 4 nonpolar bonds, so that's definitely going to be nonpolar. And if you're nonpolar, you can't have dipole-dipole. Now with CBr4, any one CBr bond is going to be polar. But what's important is in this tetrahedral shape, they end up balanced versus each other. So the idea is, with a molecule like this, now these are, the greens usually represent chlorines, but it's the same idea, is that it's like a 4-way tug of war, where they're able to balance each other out, and we get a nonpolar molecule. And this is actually the molecule I'm going to work with on my video in polarity. So if you can't see why this is, check out that one. The last case, CO2, might initially look like it should be polar. But when we do this, there's no lone pairs on the central atom, so we just get a linear molecule. So what we do is we end up where one side's going one way, one side's going the other, and they cancel each other out. Those lines should be equal length. I'm just not great at drawing. So in that case, if they both cancel, we end up with a nonpolar molecule. So asking you, are there dipole-dipole forces, is another way of saying, is this molecule polar? If it's polar, so I'll write that down. So polar means dipole-dipole. Nonpolar means no dipole-dipole. Nonpolar is only going to have dispersion. So we'll say only dispersion, which means not dipole-dipole. Now, my head, I got to get used to where my head's at. I blocked the word dispersion, but I said the word dispersion so you can know what it says. I'll work on that. I'm still adjusting back after getting back this semester. So, we've mentioned how we've got these forces that are related to dispersion forces and our dipole-dipole forces. A question that might come up that at least I think is reasonable is, so what else can we do with these things? How does this help us knowing how the chemistry of how molecules interact? Well, there's a pretty good one related to solubility. You may remember the term like dissolves like. At least for me, this was said at some point, I think, in middle school. I didn't understand why exactly. I just knew that we did some different neat demonstrations to show, hey, water and oil don't mix. It's related to this dispersion forces and polarity issues. So what like dissolve likes means is that polar dissolves polar, and nonpolar molecules dissolve nonpolar. Now, this is, the way I'm presenting it here is very binary. It's important to note that with polarity is that it's a big spectrum. Some molecules are just a little bit polar. Some are really, really polar. So as you get into organic chemistry, you're going to expand on this and you'll start dealing with, oh, this molecule's really polar, so it doesn't really dissolve this molecule that's just barely polar all that well. Or, oh, this molecule's just barely polar. Maybe we can use it with something that's not very polar at all. So just to note that we're going to talk about it in a somewhat simple term here, where we're just like polar dissolves polar, nonpolar dissolves nonpolar. It gets a little more complex as you go. But we're going to start with the simplest case of explanation. So let's take an example where I have 6. Which molecules am I working with? No, I was doing 5. I was doing pentane. It doesn't really matter in retrospect. So let's say I mix some pentane and I put it with some water. And let's look at 2 different organizations of that. Let's say in one of them, what happens is all the pentane stays up at the top and all the water stays at the bottom. So what's important here is the oxygens are going to want to be around the hydrogens. And so we're going to have different orientations. So water can organize itself in different ways. What's important is the oxygen sides are going to try to be near hydrogens, and the hydrogens are going to try to be near oxygens. And they're going to spread out, and they're not spread out. They're going to do this as best as they possibly can. I'm drawing in 2 dimensions, so I can't draw the fact they're like water molecules in front and behind as well. But what's important is the water is going to try to attract to itself because it is able to not only dipole-dipole interact, but it actually has something we call hydrogen bonding, which is a special form of dipole-dipole. But so the negative sides, the positive sides, they're attracted to each other. On the other hand, when we take the pentane at top, the pentane only has dispersion forces. So it wants to maximize that surface area because it can interact with itself, and it does that. Now let's imagine we tried to mix these up. So instead, we have our pentane. That's not a pentane. We have our pentanes, 1, 2, 3, 4, 5, and then we've got some near the bottom, we have some over here, and then you have water molecules interspersed. Well, we have a problem now. Those water molecules can't hydrogen bond to the pentane, can't bond to the pentane. They can't have that dipole-dipole or that hydrogen bonding. So, no dipole-dipole here, because that BC is going to happen, because pentane is in the way. So what happens when you try to mix these together is that's not a stable form because the water can't hydrogen bond to the other molecules there, other water molecules. The pentane's in the way. So over time, as the molecules move around, when water molecules find other water molecules, they're going to be attracted to the intermolecular forces. And over time, the water molecules are all going to find themselves, and all the pentane's going to find itself, so it can just dispersion force interact with itself, and it ends up self-separating out. So if you shake up a water to oil mixture, let it sit for a bit, it'll split up. It'll depend on which molecule is more dense, which sinks and which goes to the top, but that's the general idea. So that's why like dissolves like applies. It's because like dissolve like lets the intermolecular forces maximize. It lets there be as many intermolecular force interactions as possible. Whereas if you try to do it a different way and you try to mix them together, they don't want to stay mixed because it's not allowing the intermolecular forces to interact. So this is 24 minutes long. That's long enough. We will finish up discussing hydrogen bonding and ion dipole in our next video.